Okay, you've been there, right? You're standing in the pharmacy aisle, looking at two boxes. One has that brand name you always see in commercials, and yeah, it has the higher price tag. The other one? It's the generic, and it's way cheaper. So, what's the catch? Is there one? Today we are diving into the science to find out what the real difference is, if any.
So let's get right to it. You're holding, say, a box of Motrin, and right next to it is the store brand ibuprofen. The store brand is definitely easier on your wallet, but is it identical? I mean, will it kick in just as fast? Will it work just as well? That's the big mystery we're going to solve today.
To really answer that question, first, we've got to understand what actually happens the moment you swallow a pill. The best way to think about it is like an obstacle course that the medicine has to run inside your body just to start doing its job.
So every single pill, brand name or generic, faces three big hurdles. First up is disintegration. It has to break apart into tiny little pieces. Then, those particles have to dissolve, basically turning into a liquid solution. And finally, the most important part, permeation. The drug has to get through the wall of your intestine and into your bloodstream. Only then can it really get to work.
Now, in any obstacle course, there's always that one part that's the toughest, the one that slows everything down. In pharmacology, they call this the rate-limiting step. This one single step, whether it's dissolving or getting into the blood, becomes the bottleneck. It actually controls the overall speed of the entire process. In other words, it's what decides how fast you're going to feel that relief. Okay, so if every pill has to run this crazy obstacle course, how in the world do scientists measure how well it did? How do they figure out how much of the drug actually made it to the finish line and started working? Well, there's an official term for it, and it is the key to this whole puzzle: bioavailability. This one measurement tells us two supercritical things. The rate, that's how fast the drug gets into your blood, and the extent, that's how much of the drug actually makes it. It's basically the drug's final score on that internal obstacle course. Now, scientists can measure this a couple of ways. They could compare a pill to getting that same drug through an IV, which is 100% available. That's called absolute bioavailability. But for our question, brand name versus generic, the one that really matters is relative bioavailability. This is where we directly compare two different pills to see how they stack up against each other.
All right, we have all our tools now. We understand the obstacle course the pill has to run, and we have the scorecard, bioavailability, to see how it performs. Now, finally, we can settle this brand name versus generic debate once and for all.
The official verdict, the gold standard, it all comes down to this one word: bioequivalence. This is the super strict scientific test that regulators like the FDA use to say, yep, these two drugs do the same thing in the same way. If a generic drug is proven to be bioequivalent, it's considered a true substitute.
So how do they actually prove it? Well, scientists run these carefully controlled studies on volunteers, and they measure three crucial things: Cmax, which is the peak power, the highest concentration the drug reaches in your blood; Tmax, which is how long it takes to hit that peak; and something called AUC, which is kind of like the total amount of drug your body is exposed to over a set period of time.
And here it is, the punchline. If the generic drugs Cmax, Tmax, and AUC are statistically a match for the brand name drug's numbers, then regulators say their performance is the same, period. For all practical purposes, their safety and their effectiveness are considered identical. This test is the scientific proof that lets you save money without taking a risk on your health.
So, case closed, right? Well, not quite. See, a bioequivalence test proves the two drugs are the same under perfect lab conditions. But out here in the real world, other things can change how any drug, brand or generic, works inside your own body. And this isn't about one being better than the other, it's about how your body itself handles the medicine. One of the biggest factors is something called the first pass effect. So after a drug gets absorbed from your gut, its very first stop is the liver. And you can think of the liver as a toll booth. It takes a tax, metabolizing and getting rid of a chunk of the drug before it ever gets to circulate through the rest of your body. So that tax reduces the final amount of drug that actually gets to do its job.
And what you eat, oh man, that can have a massive impact. Just look at these two examples. For the drug tadanosine, food is a blocker. It actually reduces how much you absorb. That's why you take it on an empty stomach. But then you have isotretinoin, where taking it with a meal can literally double the dose your body gets. It's a huge difference.
And that brings us to maybe the most famous and kind of wild food-drug interaction out there. It involves a super common fruit, one that can dangerously supercharge certain medications. Any guesses?
The culprit is grapefruit. What happens is, compounds in grapefruit actually block a really important enzyme in your liver called CYP3A4. That's the very enzyme that takes that first-pass tax on a whole lot of common drugs. So when grapefruit blocks it, way more of the drug floods your system than you're supposed to get, and the levels can spike to dangerous, even toxic amounts.
Now, everything we've talked about so far really applies to traditional drugs made from simple chemicals, but medicine is evolving fast. What happens when we start talking about a newer, much more complex class of drugs called biologics? For these big, complex drugs, we don't have generics. Instead, we have biosimilars. See, a generic is like a perfect chemical photocopy. It's identical. But biologics are these huge, complicated molecules made from living things, so you can't make a perfect copy. Instead, a biosimilar is proven to be highly similar, with no meaningful differences in how it works or how safe it is.
A perfect real-world example is the biologic drug Humira, which a lot of people have heard of. Well, a company developed a biosimilar version called Julio. It went through a ton of testing to prove that it's just as safe and just as effective as the original. This is really the future of making these complex medicines more affordable. And this leaves us with a pretty fascinating thought to wrap up. We started this whole thing by asking if two simple pills are the same, and we learned the answer is bioequivalence. But as medicine gets more complex, more personalized, the very question of what the same even means is going to have to evolve right along with it. It's an incredible challenge for the future of medicine.